Okay, here we are. Weather information, class 2. So we get to put our our attorney hat away for a little bit, and this week we'll be really kind of a little bit in the cockpit. We'll be standing outside of the cockpit. We'll have a little bit of meteorology hat on. We're gonna look more at like weather sources next week, but this week I just wanted us to take the time to really look at what the DPE or the FAA thinks we should know, what the written test kind of wants us to look at, and what I really want you to kind of start to be thinking about from a weather standpoint. I've had some fun with this. I asked the club to send some of their favorite pictures of some of the weather that they've encountered or flew in. And here's one of our youth members. He was 17 last year when he took this. I remember when he took off for this flight. He was in the L-33, which is one of our nice medium performing club ships, and I was in the 126. And we were both on the eastern ridge of Hood River here, and he was able to penetrate the wind from the west into the middle of Odell and go up in a hole and get up into the wind, and my ship wasn't able to do that. I was a much slower ship. I got away from the ridge, started losing too much altitude, and I had to go back. But this is a result. He kept saying it was beautiful up there, and you can see there that he has a picture of the bow wave. Or you might pronounce it bow wave. Let me get my little spotlight here. Right there's the bow wave of Mount Hood, and we're going to learn today what these clouds are, what they're called, how they're created in the lift. So I just think that's kind of neat. And so here we go. I have to always, I think, snap off of that to be able to, yeah, that's the one issue with this. Go back to here. Okay. So, all right, again, we're here at Wildwood. We appreciate them letting us be here. We appreciate the SSA and David Lesnick for hooking us up with the webinar for this to be recorded for you to be able to access in the future. And of course, our home club here, Hood River Soaring. Remember our objectives: pass the FAA written and pass the oral portion of the FAA check ride, keep it simple, and grow our knowledge from here. Task B last week was certificates and limitations of our airplanes and ourselves, and this time we're talking about weather information, and we're really going to talk about probably section 2 and just section 3 this week, and move on to the section 1 and 4 next week. So this time we're going to be exhibiting, they want you to exhibit knowledge of Higginson of the relationship of the following factors to the lifting processes. All right, so whoops. Okay, so first, we talk about nearly all weather phenomena are due to the uneven heating of the Earth's surface, okay? And in this, the sun is going to create really for thermal soaring weather are 3 main events that we like to soar in. The convective currents, convective meaning energy going up and down, and in our case, we call it thermal soaring, or advective currents using horizontal energy, which will create ridge soaring, wave soaring, and other types of lift. That's this picture here I actually took. I'm following the tow plane there. That is the L-33 that the other guy, the other youth member, was flying. And there's some nice cumulus clouds you can see there to the right. We'll talk more about that. So remember the PAVE we talked about on our way to the airport, and we talk about the risk, we think about the risk management, and we've got, so we talked about the pilot, and on the way, make sure you have your pilot license and your photo ID, but then check that I'm safe, I'm feeling good today. We got the aircraft, and now we're to the third line here, we're to the environment. Okay, so in our environment that we're generally going to be flying in with gliders or soaring, especially around here or as at the private level, is VFR day, and that means visual flight rules. We'll get into the visual flight rules and what that means later, We're actually just going to be talking about the visual part today and the environment that we're actually flying in. And we're very fortunate here in the gorge area. We have an amazing array of weather to fly in. So first, I'm just going to kind of talk about a general, some very important weather environments about our atmosphere, or just a general, get us all in the same frame, let's all get in the same troposphere. Let me just say that as far as where we're at, okay? So let's think of the atmosphere that we're concerned with about flying in is the troposphere. It's the first anywhere from 18,000 to say 36,000 feet of air. It actually does change, and I like to think of it as a sea of air, and it starts with the least amount of pressure up towards the top, or up here in the troposphere, and it gets heavier as we get down towards the surface. It's composed of 78% nitrogen and 21% oxygen, and then a few trace gases. And then there's, depending on where you're at, there's 1% of moisture up to 4% moisture at the equator. And this moisture, known as water vapor, causes a lot of havoc throughout the atmosphere, but also provides a lot of fun for us to soar in. This atmosphere has weight. You know, whenever you read in the books or you read about atmosphere, it always talks about if you take 1 square inch of pressure at the surface, it's going to weigh 14 pounds. And then at about 18,000 feet, it's about half of that, okay? The temperatures, I found this very interesting. I went on a search, and the temperatures on Earth range from a negative 126 Fahrenheit, or that would be negative 88 Celsius at the Vostok Station in Antarctica, to the hottest recorded temperature so far has been 136 Fahrenheit, or 58 degrees Celsius in the Libyan desert. For some reason I thought it would have been a much higher temperature, but and again, the troposphere is elliptical shape due to the gases, or how hot the atmosphere gets at the equator. It can change, and then as it turns through the year, the shape of the troposphere, the shape of it changes due to how the heat of different parts of the Earth. There's a tropopause here. This is a boundary layer that actually traps our moisture, or our atmosphere that we fly in. It traps it in so it doesn't actually go up. Once you get into the stratosphere here, moisture and the temperature stays more flat, whereas ours varies down here in the troposphere. But the tropopause is interesting. Due to that temperature variance at different parts of the Earth, it kind of moves around and massages our atmosphere, and it has a big play on where the jet stream lays. And that jet stream, as you're going to see, helps us here in Hood River have a lot of fun with our soaring adventure. Any questions about the troposphere? Okay. Oh, so the next thing is atmospheric circulation. A general principle that we're going to see throughout talking about weather is air always likes to seek out lower pressure. And on the equator here, the hotter part, so light, as air gets hot, it gets lighter, it gets less dense, it likes to rise. And so the theory here is that the temperature, the hot air rises and it'll go back to the poles, and then as it cools off, it comes down, right? So here's our simple circulation, or our simple convection model of the sun radiating on the equator, going up to the poles and coming down. So this constant motion is what creates a lot of our advection, or our wind weather. And so what happens is, instead of this simple model of just one big gigantic flow, we've got 3 main flows that the air gets deflected from the turn of the Earth. And so this first one, the Hadley force, as the temperature heats up at the equator, right, it likes to rise, right, and it'll travel north, and it'll get filled in. The cooler air will fill it in. Okay, everyone, this concept's making sense. Yes. Okay, so the I find this very interesting to look at as the Earth turns this way, and these winds cool off and come down, and then they fold back under right here, and that's what, as you heard of, the easterlies, or the tropical easterlies, because they're warm. And then, whoops, lost my mouse here. Then you got the feral, or creating the westerlies, and this happens where as this comes down and it's this cooler air, and it's mixing with this hotter air, and that's how we get those what they call westerlies, or prevailing westerlies, out of the southwest in the United States. Then, of course, yes, go ahead. I think actually it has to do with the two jet streams. I believe it has to do with the tropopause. That's what I've seen in my studies. But other than that, anyone else have any ideas on that? Yeah, I've seen that too. Yeah. The question for those online, or was there any questions of why these were by 30s, at the 30 degree latitude and the 60-degree latitude, and so I've actually read about the polar jet stream and the continental jet stream, but and it could be just as simple as Gideon is suggesting, that it's just easy to divide it into thirds. But the next part I really kind of want to discuss with this, right? So as you've got the air up high, getting used to my new little computer here. As you got the air up high with these different easterly winds, these westerly winds, as you continue from the high part of the atmosphere all the way down to the bottom, you have frictional forces, right? And I mean, we've already seen some of these frictional forces here, creating these easterlies and westerlies, but and you can see it all the way down to our local level, like even at the airport, you know, when we're watching just like the windsock, and how much what is the wind doing. And so up high, the wind can be doing one thing, but the geographic regions as we come low, or the orographic regions, play an important part on what happens to the wind patterns down low. Just like today. Yeah, so thinking the question was just like today. So what went through today? A Chinook wind? And what is a Chinook wind? Right, yep. And there was a cold front that went through a little bit ago, and there was actually there was a low pressure system that was through as well. Yeah. Yeah, today was really fascinating to watch outside the window. Here's our first question. The wind at 5,000 feet AGL is southwesterly, while the surface wind is southerly. This difference in direction is primarily due to A, stronger pressure gradient at higher altitudes, B, friction between the wind and the surface, or C, stronger Coriolis force at the surface. And that is B. Does that make sense for everyone? Okay. All right. Moving on to wind patterns, and talking exactly what we're talking about, leading on to what we were just kind of talking about today. High pressure systems. So we'll be looking at more, you know, how to read meteorology charts and things next week, but just put that on there as an example. So, oops. high pressure systems. So they usually bring in areas of dry, heavy descending air. They move clockwise in the northern hemisphere, and they're just typically associated with good weather. Low pressure systems are they move counterclockwise, and they tend to move up, and then as they are moving up, meaning up in the atmosphere, cooler air can rush in. And so generally low pressure systems are when wind come in. And so that's why, as today, we had that low pressure system moving through with the cooler air, and we had a lot of winds down on the river as well. Let's see, what else do I want to say about this? Typically associated with bad weather. Any questions about that, Bernard? Oh, for the term, it's yes, there is, and I'm trying to think. Right, it's hurricanes, and there's do they might be local, but there was another reason. Counterclockwise, cyclonic. Trying to think what that was. Let me stew on that, and I'll come back. I'll think of what that was. But the okay, first task. Moving on. So, all right. So they're going to talk to you about pressure and temperature lapse rates, and so lapse rate, that's a change in air pressure or temperature with altitude. Okay. And so here's our basis for the International Standard Atmosphere said, all right, 15 degrees Celsius or 59 degrees Fahrenheit. That's our standard temperature at sea level. Pressure, 29.92 inches of mercury, or 1013.2 millibars. Generally, we see pressure is how we set our altimeters, and I've got a picture of that for anyone that hasn't seen one here in a little bit. And generally on charts is where you'll see the pressure as millibars. The overall riding principle here is that an increase in altitude will be a decrease in pressure and a decrease in temperature. Occasionally, we'll get temperature inversions, and we'll talk more about that. So let's first talk about pressure lapse rates. For about the first 10,000 feet in our atmosphere here, we generally lose about 1,000, or we generally lose 1 inch of pressure for each 1,000 feet. And if anyone's curious about how we got our pressure for mercury, here's a mercurometer, and so generally you just set a little. This will be calibrated to 29.92 inches of mercury, and as the atmosphere changes, it'll go up or down. I just find these kind of fascinating. But anyway, effects on as we go up in the atmosphere, or as the pressure decreases, those have tremendous effects on our aircraft. And when we get into the instrument section, we'll see that. Again, our altimeters are set by pressure and mercury. And again, the weather charts are shown pressure in millibars. You can see here, I've got the sea level pressure, 29.92, and just each inch of mercury as it goes down is about 1,000 feet. So if any of you have not seen an altimeter, this is on the left, the altimeter, and here's a calibration window, generally called a Colesman window. And on this window, you would, use this little bar over here. You'd call into your FBO or your local weather station, and it'll tell you what the pressure is. And so you'll change that to the pressure. And then here's a cockpit, and so I just kind of threw that in there for anyone yet that hasn't been flying. And there's the altimeter. It sits there. I just wanted to put this chart in here, which just shows sea level. There's pressure in inches in mercury, and here's the millibars. And I just kind of because I found millibars when I first started working, when I first started learning about weather and stuff, I found millibars very weird. So I just kind of put this chart in here for people to kind of visualize a little bit what it would mean for them. Because see, here's 1,000 feet, so we've lost an inch of mercury. We lose another inch of mercury. There's 2,000 feet. We lose another, and then here we are. So 1,000 millibars, 900 millibars. There's nothing really here like you need to memorize. I just wanted people to see. Some people are visual learners, and the area we play in a lot here in the gorge is up to around 10,000, 13,000 feet. So we'll see quite a change in pressure and millibars. Okay. So now the second part of that is the temperature lapse rates. Now, again, the standard atmosphere temperature lapse rate goes down 2 degrees per 1,000 feet, and we really use this as a way to compare what happens with the atmosphere, right? So here we are, sea level, and so if we go up to 4,000 feet, losing 2 degrees each, right? The other temperature we're concerned with as glider pilots is the actual lapse rate, or the environmental lapse rate. And this is found by sending up a sounding balloon, which happens 2 times a day now. And it used to be done a lot more at different places. Salem does one at 5 a.m., 5 p.m. every day. There's one in Seattle. I think Eugene surprisingly may do one because they're so close together. But these are also done by aircraft, by infrared on satellites, and things like that. And this is, again, just to track what the temperature and the pressure of the atmosphere is doing. And here's a SKU-T chart. Now, we're going to learn a lot more about this as we go along, but right here, this red line is the actual temperature. That's an actual balloon sounding. Okay, so it's getting the temperature from the 1,000 feet all the way up. And then on the right here is what the wind is doing. And so the direction that it's from, these are kind of a northeast direction, right? If they're pointed straight up like these ones are, that's from north. And bars on here are weather, okay? So again, if this was the actual temperature, this is what we're seeing on the red line on the SKU-T. As we go along, we're going to learn a lot more about the SKU-T and how to use it. Okay. Oh, it's hard to see that? Okay, I'll make sure I switch to the red line for you, Doug. So pressure and temperature lapse rates. One of the things that we get concerned with, definitely with aircraft, is how hot it gets. And and we call this density altitude, right? As temperature gets hot on the ground, like you're at the Hood River Airport, we're at 600 feet, we're at a certain pressure, and as temperature goes up, pressure gets less, okay? So, or density gets less, sorry. The pressure stays the same. As temperature rises, density gets less. And for us as pilots, that makes a big difference on how our aircraft perform. On a hotter day, your aircraft, it's going to take a longer amount of runway to take off because we have less density. As glider pilots, we're not so concerned about it to a point, but your tow pilot really is, because he could run out of runway. And so if anyone's having trouble with this concept, you know, it requires a certain amount of molecules or air for our wings to go over and get airborne to fly in. And as that air becomes thinner and thinner and thinner, it takes a longer amount to get all those molecules to take off. And we have charts for that called density altitude charts. Again, we're going to study more, look more at this on the next one, but since we're here, let's go through an example of the density altitude chart. So remember I showed you the altimeter, and you would call up the FBO or the AWOS, which we'll learn what an AWOS is. It's an automatic weather station, and it would report the altimeter on there. And in this example, we're our field elevation, remember, we're Hood River, we're at 632 feet, and we call up our AWOS, and it tells us it's 28.4. So we go up here to 28.4. I always find this chart odd to read because since I'm English and I always want to read from left to right, I always feel like I should be starting over here somewhere. But the reality is they're all made this way, and we start over here with the altimeter setting. Okay, so 28.4 Mercury, and you just simply read over to the conversion factor. Okay, and so here it's 1436. So we would add those two together and we get 2068. Okay, and so then the outside air temperature is next, and the AWOS would give you the temperature. So it's telling us it's 32 degrees Celsius or 90 degrees Fahrenheit, and we would take that up to 2068 right there, and then we would go over this way to this line. And so it's, you know, about 4,200 feet out. So that's how our airplane is going to behave, right? We're at an airfield that's 632 feet, but it's gonna feel like it's taken off at a field that's 4,000 feet. So we're going to use more runway, as we'll see in some performance charts later. You'll be asked to do some simple, probably one or two of these on the FAA test. Anybody having any difficult understanding that, how this works? Okay. Pretty simple, may take a few practices. If anyone ever wants to spend more time with it at home, let me know. Okay, I gotta click off the little button here. Okay, I'm getting good at this. All right. So again, just want to reiterate that hot temperatures, high pressures, or I should say a pressure altitude setting of that starts to go into the 20s can be hard on aircraft and the performance of the aircraft. Next, atmospheric instability. What we're really talking about here is vertical motion. Warm air rises, cold air sinks. Okay, and so a stable atmosphere resists vertical motion. Okay, so and an unstable atmosphere is going to promote vertical motion. In a stable atmosphere, if you try to heat some air and it doesn't, and if it tries to move up, it'll put it back down, right? So cool, moist days resist vertical motion. Whereas an unstable day, if it's a cool day and a parcel of warm air that's warmer than the air surrounding it, it'll rise. Okay, buoyancy. So just think about like a ball in a water. To move on, the temperature. So we've talked about a stable, or not. I'm sorry. We've talked about the standard atmosphere that loses 2 degrees per 1,000 feet. Okay. Now the fun starts with what we call dry adiabatic lapse rate, right? Adiabatic is adiabatic cooling or heating is really a term of where you lose heat, or I'm sorry, when you decrease pressure, you lose temperature. Okay, so as in our own atmosphere, as you go up and you lose pressure, right, the temperature should cool off. Okay, and an adiabatic, lifted air loses temperature at a rate of 3 degrees Celsius. Okay, per 1,000 feet. And in an example here, if we took this, oh, sorry, Doug. If we had a day where it's 15 degrees Celsius, okay, and the sun came out, and this was the Rose Hours parking lot, and it starts heating up, and 50 feet above the ground, it gets hot. It'll get hotter than all the air around it, and it'll start to go up, right? And if we look at the 1,000 feet, it's 14 degrees Celsius, and it's warmer than the air around it, right? It's going to keep going up. And at 2,000 feet, it's warmer. It's going to keep going up. And at 3,000 feet, it's going to keep going up. 4,000 feet, it's going to keep going up. Okay. So what I'm showing you here, that this is an unstable atmosphere. Okay. And if we look over here between the one that I called stable, you can see that at 2,000 feet, this parcel would stop rising. So this is a stable atmosphere over here, the one that's decreasing at 2 degrees Celsius per 1,000. Whereas this one here is unstable. And this one here is unstable as well. This one's losing 4 degrees per 1,000 feet. Okay. All right, so here again, the red line, right, is our actual environment, and the tan or yellow line on there is the dry adiabatic rate. A dry adiabatic atmosphere loses 3 degrees Celsius per 1,000 feet. Okay, so any SKU-T chart, just showing you, this is a standard on the SKU-T chart, and I'll show you how to use that here soon. Okay. All right, let's add humidity to the atmosphere. Okay, so water vapor. Again, humidity is the amount of water vapor present in the atmosphere at a given time. And dew point, given in degrees, is the temperature at which the air can hold no more moisture. Okay, so that means the air is completely saturated. And what we want to talk about here is that lifted parcel of air. It may not keep going up if it depends on the dew point, right? At some point, it could become saturated with water. So in this example here, if the dew point, so a dew point, sorry, there's a dew point temperature convergence rate of 2.4 degrees Celsius per 1,000 feet. And this is how we figure out, or we can make a guess of where the cloud base is going to be. Okay, so if you look at this lifted parcel of air, that's the same one. And I've put it here, I put it both in the Fahrenheit and Celsius because the questions on the exam they always give them to you in Fahrenheit, even though all the other questions are in Celsius. So the lapse rate for your dew point is 0.55 degrees Celsius or 1 degree Fahrenheit per 1,000 feet. So you can see I've given you this dew point here. It's 46 degrees. Okay. So as this starts to decrease, these two will meet at 4,000 feet. So the cloud base for that day is going to be about 4,000 feet. Okay. Correct. Correct. So if you know the temperature of the day, or even the current temperature, and you know the lapse rate, so you could subtract those two and divide them by the convergence rate and get the cloud ceiling. The right. Exactly. Yeah. The correct. Because as the pressure, because as pressure decreases with altitude, right, the air holds less moisture, and therefore the dew point's going to decrease with altitude. Okay, and the lifted parcel of air, its temperature is going to decrease faster. It's going to decrease at that dry adiabatic rate. Okay, so it's going to and so as it's decreasing at 3 degrees Celsius per 1,000 feet, the dew point's only going to decrease, at a, 0.5, a half a degree Celsius. And so at some point they'll meet and the cloud base will start, right? Because the yeah, well, that's what they'll do. The other part to instability is once they do meet, that temperature is that you have clouds, the air is saturated, right? So it's going to decrease much slower because when condensation happens, right, you have latent heat. So the water comes out and it releases heat, and now it's going to decrease slower. Okay, and that's what we call the wet adiabatic lapse rate, and it changes at a rate of 1.2 degrees Celsius per 1,000 feet. And then your atmosphere gets really stable. And so like if you did an example here where you just had a wet atmosphere to begin with, this lifted parcel of air doesn't get much above 2,000 feet. Here's the wet adiabatic rate on this side, decreasing at 1.2. And then here's a standard atmosphere, right? And then here's the dry adiabatic rate. Have I thoroughly confused you all? So backing up, the most important thing about this, warm air rises, cold air sinks. Okay. Dry air, the dry adiabatic lapse rate decreases at 3 degrees per 1,000 feet. Okay. And once it's saturated, it changes at 1.2 degrees. Okay. Those are the main things to take away from that. Yeah. So yes, what happens here, the red line is the actual. And then if you had, let's say you were forecasted um, let's say the forecast for the high of the day, let's say the forecast high of the day was 20 degrees Celsius, right? Then it would cool, then it would cool by, the dry adiabatic, and anything in front of this would be expected to create thermals in front of this temperature. That's millibars. Yeah. Okay. What is the equation for finding cloud base that you just explained? Hey, Ian. So let me. Oh boy, how do I close this? Okay. Okay, so this will address Ian's question, and then we'll start into the thermal part, which I think will clear a lot of this up. And the next time I give this lecture, I know how to simplify some things to make it way simpler. At approximately what altitude above the surface would the pilot expect the base of cumuliform clouds if the surface air temperature is 82 and the dew point's 38? Okay, so the trick of this is we knew that we know the convergence rate. Okay, everyone's taking a guess here. Everyone's calculating. You want me to wait? Oh wait, so I can go back. Here's the convergence rate. 2.4 degrees Celsius or 4.4 degrees Fahrenheit. Okay, and so then your answer is 10,000 feet. Cool. Correct.
So the difference in temperatures is 44 degrees. And that
Right. The difference is
will be met at 10,000 feet.
correct. You understand? Did you get that, Gideon? Okay.
You got to cool the 82 degree air down to 38.
Correct.
You got it. 4.4 Fahrenheit per thousand.
Exactly. Well, yeah, because the dew point. Well, the
difference between the closed.
exactly. Yeah. All right. Here's the next one. Which conditions result in the formation of frost? A, the temperature of the collecting surface is at or below freezing when small droplets of moisture fall on the surface. B, the temperature of the collecting surface is at or below the dew point of the adjacent air and the dew point is below freezing. Or C, the temperature of the surrounding air is at or below freezing when small drops of moisture fall on the collecting surface. B is right. Frost forms in much the same way as dew. The difference is that the dew point of the surrounding air must be colder than freezing. Right. Exactly. Exactly. So just quickly, we'll look at this stuff next week, but this is the hourly forecast graph, and I took this. I took this screenshot here because I was interested in what the weather was going to do at 9 a.m. the next day on Friday, and the temperature and the dew point are both 33, so I was expecting it to be clouds. And I'm sorry. Yes, yes, those correct. And so here's when I took that screenshot out my office window. Here's the next day. That's outside my window of my house that same time. Here's the Ken Jernstedt Airfield AWAS. You can see the temperature's 36, the dew point's 34. So we definitely expected fog at that time. Okay, so hopefully this will start to clear some stuff up. Thermal index and thermal production. Okay, elevator of fun. That's what it is. All right, so a thermal, it's an air that is heated and rises in a column or bubble. And so warm air, less dense, it rises, right? And continue to rise as long as it's warmer than the air around it, okay? And this is a nice little model here on the left, okay, that air rises. This is, so I like to look at this chart as this is developing during the day. This isn't a series of mountains in a row, okay? So the thermal's developing, it's getting warmer, it's developing, moisture's, it's meeting its convergence point that we talked about. And then here's where it starts to die at the end of the day and the wind's going down. So they expand as they rise. They have a life cycle, as you can see, minutes to hours. How high? That's going to depend on the convergence point or an inversion, right? We kind of want an inversion with thermals. Because otherwise they could just develop into thunderstorms. Everybody knows what an inversion is, correct? That's where the temperature, instead of gets cooler as the altitude goes up, it starts to become warmer. And cumulus clouds are an excellent indicator of thermals. All right, so here's our next picture. So column versus bubble. There's all these pilots out there. They debate what are they doing. I think they're probably both right. On the far left there's a column. You can see it widening and mixing with the air around it. The picture next in the center is the bubble idea, as maybe a bubble heats up 50 degrees below and then breaks away and then goes up, and then maybe another one heats and breaks away later. On the picture on the right, columns are kind of more associated with, we've found, with kind of large either mountain face sides or rock ridge sides, and bubbles kind of tend to maybe be from fields and things like that out, you know, with the farmers farms and things like that. But they can also be free. They can be anchored, like this picture is showing, or they can kind of grow up and hit up to the convergence point and just kind of cruise along. When I was just in Arizona, got to do a little bit of soaring, and I think I experienced a moving free column and an anchored column, both in the same flight. I was released on this north part of the field, and there was kind of a big ridge that was like a Y, and it was like a, yeah, and the field was, and the plane took me over here, and there's this big ridge here, and the wind was coming out of the north, and but the winds were starting to dive down, and I was over here, and I could have swore there was just bubble just kind of floating along, and I kind of found it, because then I went back here, and it was gone, and then I went back around this way, and I kind of found it again, and it kind of died off. So then I had to go over here, and there was this other little ridgeway in here, and there was kind of a column just staying right there, and I was able to just stay with it for a while. So I think I experienced both that day. And they can have multiple cores. It could be a single core, but it could have multiple cores, different shapes, concentric circles. Air masses conducive to thermal soaring. So the ideal is the recent passing of a cold front with the building of a high pressure system. Because again, when we talked about the high pressure systems, they start to move down in the atmosphere, and as they're building, that keeps an inversion somewhere around between 6,000 to 10,000 feet, which creates good thermals, but prevents that thunderstorm from growing. Too much moisture aloft can, though, give us high cirrus clouds, which will reduce surface heating and won't produce, allow thermals to produce. The best thermals have a flat kind of concave base to them, dark edges, and those are kind of indicative of the strongest lift. You can, in this picture here, you can see the, this is what we call a cloud street. Down here. And this is our eastern ridge. And these are cumulus clouds, which underneath would be kind of flat. And when you're soaring out underneath here, these have good lift underneath them, and then you can take this cloud out underneath here, and if you're lucky, you could penetrate up through what they call the boundary layer, or where the inversion layer sits, and get up into the wave. And here's one of our gliders. This is Tim, and the picture's taken by Kelly. And here's wave clouds. But they first used this cloud street to get up in there. So here's a bunch of thermals layers that have all packed together to create that. These can thermals I've experienced without the clouds here, and in streets like this, they're called lift lines. They're kind of hard to find, but sometimes there's been clouds here, and I don't know why, but there's sometimes the lift will kind of lead you out there, and you'll just be able to kind of keep going, and it's just clear. And there's a great series on SSA, the Soaring Society of America, right now under webinars, that's about cloud streets and lift lines. And so thermals, you know, obviously they exist without the clouds above them. The clouds just show us where the lift is for sure. So, well, that's the trick. That's the magic trick, right? Sometimes, that's a fair question. The question is, for those listening, why does this thing not? This thing should go away, right? Okay. The question was, how do you go up through it? I love that you asked that, Gideon. So, you know, if you're lucky, right? Because these are thermals being created here, right? These thermals just happen to have enough moisture underneath them to create that cumulus cloud to show you where it was. But there may be a spot with thermal air rising above that cloud. And if you get lucky enough to find that, you could go up that. And another thing here, this day I know was also windy, in that maybe with the push of a thermal and the orographic region, that you might find kind of an elevator spot. You know, maybe it's hitting, you know, because this is middle mountain right there. Maybe they got lucky and found a spot that just had a little more push. You know, we'll talk about ridge soaring here in a moment, but that's the magic question. Okay. All right, so here again, our examiner says, hey, what is the thermal index? We were just talking about thermals. And so I'll give you the little definition here. If we subtract the temperature of the rising air from the temperature of the air through which it is rising, we have a measure of the strength of the thermal of that altitude called the thermal index, right? So, and we need a -3 or greater for your glider to rise. Let me show you. It's probably should have started with some of this and would makes the dry adiabatic make more sense. So here's a simple skew T on the left, okay? And this line, sorry, Doug. Here's a simple skew T on the left. This line here represents the actual temperature, or the red line we were looking at in those other diagrams. And you simply take the maximum surface temperature and you run that, you apply the dry adiabatic number to it. It's just a theoretical line. And then in all those other lines, it's just, you just follow the dry adiabatic, right? Probably for me to start here and work backwards would make more sense, right? And so over here, I've taken that sea level and I've taken that measured temperature. I kind of made one up here, right? But I did use the standard temperature. Let's say the maximum for the day was 25. So if we subtract 25 from the measured temperature, we get -10. That's a strong thermal index, okay? And so if the examiner says, what is a thermal index? You're going to tell me, and what numbers do I need? Well, you need a -3 or more to carry your glider, because gliders on average sink at 2 knots per 100, per minute per 100, 2 knots per minute, right? And so you need 2 knots or more lift to really stay up in the air. And a thermal index of -3 will provide you the lift you need, okay, for a thermal to carry you up. The thermal index, the strength of a thermal has to be -3 or greater, right, to provide lift. And then once you get, so everything over here would provide lift until you got to 6,000 feet, and it wouldn't be strong enough to provide lift, okay? Oops.
And so that,
Yep.
this table,
This exercise here.
that only says that we can't get thermals. We can't write a thermal above 6,000 feet.
Correct.
That doesn't preclude the possibility of still finding a way higher than 6,000.
Correct. Correct.
Yeah, this assumes a particular temperature at a particular spot. Yeah, so yeah, you may move a mile over and find a little bit of
Exactly.
Or a different kind of light.
Exactly. So for those of you not in the room, the question is, what was the question?
Basically, once the thermal index is above -3, that's not like a boundary.
Right. That's right. Correct. This is not a boundary, meaning you could move to a different location somewhere else and it changes. Okay. Oops. Okay, so here I made an example where here's the measured temperature, you can see the forecast maximum, and you don't get as high. So this would be your example. You move somewhere else and it gets worse, right? It gets worse. Okay. Yeah.
Why is the surface temperature changing?
Well, great question, right? Because this is all this this is all like an interesting part of what a thermal index is like the surface temperature. You could be measuring like Rose Hours parking lot. You could be measuring like the yard and Miss Smith's yard. You could be measuring yeah, it's just like anything or totally random. The measured temperature is always just going to be whatever I mean, there's that can change by whatever front comes through that day. What the yeah, but this the forecast maximum always follows the dry adiabatic rate. Okay. So and that's why like when I was first putting my head around SQT, you always have this actual and then this maximum surface temperature. But it could be different anywhere. It's kind of hocus pocus. I mean, the main thing for the examiner is, well, what is the thermal index? Well, it's a subtraction of the maximum. It shows you the strength of the thermal by subtracting the maximum forecast and the measured forecast, right? And as long as that number is -3 or stronger, then you can have lift. And once it becomes less than -3 or starts to become over positive, then you don't have any more lift. Again, these are found by atmospheric soundings, forecast models. And okay, so we dig it again into our example here. This is the SQT, the log. So on the left, pressure in millibars. Down along the bottom is temperature. The red is the actual temperature. Blue is dew point, or not, sorry. Blue is, yeah, it is dew point. And these yellow lines, are you able to follow that, Doug? These yellow lines are the dry adiabatic rate, and these green lines are the convergence rate. Okay, so let's make an example here. The forecasted high temperature is 21 degrees, so that would be right here, right? And so if you plot that, then you would follow that dry adiabatic rate, right? Let's say you measured, I don't know, the golf course, and it's 30 degrees, and you would use that and follow it this way because you'd be following the dry adiabatic rate, okay, right? And so on this particular day, the blue was here. Well, here's the dew point, and if we take it and we follow the convergence line, the green lines, they would meet there, correct? From the dry adiabatic rate of 21, with the forecasted temperature at 21 degrees, and the green line is the dew point was 3 degrees. They would meet there. Your cloud base here would be, what's that? 800 or 800 millibars. So about 6, yeah. So that's one way for you to look at and be like, okay, there may be my cloud base, right? And then if you subtract everything that you plotted on this adiabatic rate up to there, you could say that's my thermal index. And you can see that it's going to be potential out there for lift, right? Well, I would think that in this particular case, if the cloud weren't solid, which then I would think the dew point line would be over here, that no, you would still have lift above the cloud base. Right. Everybody agree with that? What are the purple lines? Of course, Ian, I knew you'd ask what the purple lines, Ian. Ian, the purple lines are actually the wet adiabatic rate. So, so back to our example, Ian, if the forecasted line was 21 degrees, so we'd follow that dry adiabatic rate, okay? And the dew point and the dry adiabatic would meet here. And then at that point, you would follow, the atmosphere would pretty much start to follow the temperature of the purple line, which is the wet adiabatic rate. It's QT. No, no. The key thing really, boil it down. The key thing really is what is a thermal index? A thermal index is a measure. You know, again, it's the measure of the strength of the thermal, and you have to have -3 or greater for your glider for the thermal to be strong enough to lift your glider. Okay. So now, my favorite SKUT site, I wanted to show you that, and I went to it, and the government shut down, and it is shut down. But fortunately, all the other models are still working on it. Now, here's what most people do. Thermal index. This is the Tucson thermal index, right? So they go to this page, and it's all, they just take out the SKUT for you. Height of the -3 index, right? Now, we're in cold temperatures, so this isn't providing us with good information right now. Top of lift, 3,800 feet. Tucson starts around like 1,500 feet, right? And max temperature 69. So what they usually do is they have this first usable lift temperature, and they'll usually tell you, like on a good soaring day, this, 6,000 feet would probably be like -6 or something, right? So, and it'll give these trigger temperatures, first usable lift, and it'll give you the temperature. And so then let's say it said, well, it says 73, and this is a summer day, and you can just watch your temperature. All right. Or you watch the forecast. It says, oh, it's going to be 73 around 11 o'clock. Well, I'll maybe go get my glider out around 10:30 and be ready to go. Yes, sir. That is surface temperature. Yeah, that is surface temperature.
So they're listing altitudes in ASL. Is that just a weird way of saying above sea level or average sea level?
Yeah. Yeah, it's government. Yes. Yes. And so here's the Boulder, Colorado's one, what it looks like. So if the trigger temperature of 29.9 is reached, then the thermal soaring index for today is poor. They have time of trigger temperature. So, I think these are here, right? These models are here right now, but it's that we're not at temperatures where it's really useful because no one's getting their glider out right now. Correct. And so I'll need to collect some in the summer for a winter class. Okay, so, and this is as hard as it gets for your test. The development of thermals depend upon solar heating. Okay, so you can sit through me for torturing you for 2 hours, or you could just answer a simple question. Okay, all right, so a little bit of fun to break up some of the monotony before we get to the second part of the class. This is a cloud street here. I remember this was one of our last big soaring days of this year, and we had 5 gliders up. Yes, having a blast. And no, this was November. Here is I think they were in the Grove. There was like 5 gliders up, but you can see this beautiful cloud street right here, and we were able to just go so here's downtown Hood River, here's the gorge. I mean, we were able to just go from one side to the other, and and you'd get up into here, and then you'd find some sink, and you'd just come back around here and play, and this is where this perspective is of the pictures from somebody up on the ridge. And the next one, oops. Okay, that's me and Victoria up on the ridge, and looks quite overcast, but this is partly ridge lift and partly thermal activity that's going on, and this is someone in the 232, and then here's our 126 being taken a picture of, so you can see there was, and so here's Odell down here in the valley. But it was just booming that day. You could just stay up all day. Okay, cloud formation and identification. Well, we kind of already discussed this a little bit, right? The temperature is going to meet the dew point up in the, so clouds, they're either composed of water droplets or ice crystals, and it kind of really just depends on their altitude. So elements they need are, they need to form on some type of small particle, dust or smoke or salt. And again, they'll form when they condense at the dew point, when the dew point meets the dew point temperature. The part you'll get tested on in the FAA written test is classification by height range. And so just quickly to go through them, low clouds, surface to 6,500 feet, fog. The FAA loves fog. There's going to be tons of questions on fog, usually comprised of water droplets. This is where your stratus clouds are, and where your around here, our cumulus clouds are around the 3 to 4 to 5,000 range, up higher, obviously. And then the nimostratus, which means rain cloud, is down there on your right side. Then middle clouds, 6,500 to 20,000 feet. And then the high clouds, the cirrus clouds. These clouds don't really bother us, other than they minimize the heating of the ground, and these are the ones made of your ice crystals. Here's the cumulus cloud again, which we love. So again, indicate the presence of thermal lift, air that is heated by contact with the warm ground rises to a level where the decreasing pressure and thus temperature causes water vapor to condense and form the cloud. If the base is the bases are generally flat because the parcels of the thermal reach the dew point at the same altitude during their ascent. Unstable atmosphere can allow for towering cumulus clouds with significant vertical development becoming cumulonimbus clouds. Again, so without any type of inversion, that's when they can keep going and become turn into a thunderstorm. Lenticular clouds. Okay, so these are higher middle clouds. These are the ones that indicate wave. And so these are results of high winds deflected off mountains, and we'll talk about that. And so this is as air is going through these clouds very quickly, oftentimes as high as 50 miles per hour or even more. And so there's often called Lennies. Cloud caps, you'll see them over the top of mountains. Okay. It's going through. It's going through, and so it's bending. Where's my little spotlight? So it's bending. I'm glad you asked, right? So at the beginning of it, and this is again, this is adiabatic cooling here. At the beginning of it, it's cooled up to that dew point, and then when it comes out, it's warmed up. It's adiabatic warming, and it's at different levels, right? So there's many different levels there. So crests of standing mountain waves may be marked by stationary lens-shaped cloud known as, okay, good. All right, fog. Like I said, the FAA loves fog. We all know fog begins around the ground, and it occurs when air near the ground cools to the dew point. Water vapor in the air condenses and becomes visible, right? And classified according to the process that cools the air to the dew point. The FAA written test is in love with fog, and again, so you guys are a little. It's a little bit unfair. Like when you go to take the FAA written exam, they like to ask again a lot of questions that are kind of geared toward power privates, and that's another reason why they do a lot of fog questions. But pilots can get into trouble with fog, and so that's why they really want you to know about it and what causes it. And one time I was coming back from Pendleton on a cross country, and it was getting a little bit late, and I called into Hood River. I was at the Dalles, and I called into Hood River just to see what I listened to the AWOS to see what the temperature dew point spread was, and because generally when they start to get within 5 of each other is when fog can start to develop, meaning 5 degrees of each other. And they weren't quite there yet, because otherwise I was going to go ahead and just land at the Dalles and not come in, but they were still separated, and so I made the decision to go ahead and come to Hood River, and things worked out. But and we did have a couple glider pilots that they were up around Hood quite high, and they actually got stuck with a fog situation on the ground, and then it ended up having to land out in a field. So some anecdotal stories about why we need to know about fog. So we'll quickly go through this. Radiation fog forms in low-lying areas, valleys on clear nights, and little to no wind. Occurs when the ground loses heat rapidly, right? It's a hot day due to radiation, and the air directly above the ground cools to below dew point through contact with the ground. you'll likely see a radiation fog question. Advection fog, horizontal movement of an air mass from one location to another, forms when a moist air mass cools to the dew point as it moves over cooler ground or water. We've all been to the coast and seen this type of fog. Yes. Upslope fog forms when moist air mass is blown up a terrain feature and cools as its pressure decreases. I've seen this before on Mount Hood. And then we've got the steam fog, which can happen over bodies of water during the coldest times of the year. This one's interesting because it can cause low level turbulence and icing on aircraft. Starts to be your questions. What situation is most conducive to the formation of radiation fog? A, warm, moist air over low flatland areas on clear, calm nights. B, moist tropical air moving over cold offshore water. Or C, the movement of cold air over much warmer water. A, good job. Okay, and the second one, in which situation is advection fog most likely to form? A, warm, moist air mass on the windward side of mountains, an air mass moving inland from the coast in winter, a light breeze blowing colder air out to sea. Was it A? B, advection fog forms when moist air moves over. I was going back to help give you a hint there. Okay. All right. So study your fogs. Okay. Frontal weather. I love this graph because it shows how big frontal weathers can be. Fronts. So fronts obviously mean changing weather, and we had a couple today. So warm fronts obviously generally originate in the tropics, tend to be moist. They move much slower at 25 knots. As this picture shows, they'll kind of slowly creep up over on another section, and they'll slide on up over cold air. You'll see out. I saw this yesterday, actually. No, Monday. The cirrus wispies way up there, and I wondered if a warm front was coming, but I think we kind of got taken over by that cold front. So you'll see the cirrus wispies way out there. It's kind of interesting because this shows like a warm front like 600 miles back, how big they can get. And there will be mixing of the air, right? The cold and warm air. And then you'll start to get the nimbostratus clouds putting rain down. And then as the warm fronts pass, you can have a few days of lots of clouds, possible low visibility, fog, rain, drizzle. Flying through these different layers here can be turbulent, can have lots of turbulence just due to the air mixing. Wind shear for non-pilots, just winds, two adjacent winds going in different direction, which can cause pretty scary turbulence. And then the next is the cold front. Now, cold fronts are much more bold, quicker moving, 20 to 30 knots. They kind of come in steeper and just steamroll on in. Cold fronts, you start to see big cumulus clouds, and then generally a big, could be a thunderstorm coming through. Obviously, wind force is generally a little heavier, or stronger, I should say. And then on the back end, you'll usually have a few days of really clear air. High pressure systems sometimes will lot of times follow a cold front. And at first that's good because that will create an inversion layer as it keeps warm air there. So the cumuluses don't get too big and create a thunderstorm. But we don't really have that problem here up in the Northwest. I think that tends to be more of an issue for some of the plain states and some of the southern states with the deserts. The thunderstorms aren't that great here. I don't know if any of you've been to the Midwest or the Southeast and seen really, really big thunderstorms. But I think in my 7 years here, I've seen lightning maybe 7 times. It's been pretty wimpy, although it has started major forest fires, so it still can do the damage. Stationary fronts. That's kind of so stationary fronts. Back to the upper winds, that we were talking about earlier with Coriolis effects. So the jet stream and the upper winds keep fronts moving because they work perpendicular to each other, and if they start blowing with them parallel, they'll stall and become stationary. And I wondered if that's what we were starting to have this morning, because it got really warm here, even with that cold front that went through. But they can last for days, and the temperature, and so you'll just have you can have just lots of rain or fog or just air that doesn't change. But then you got occluded fronts. And the only reason, these aren't questions that the FAA guy is going to ask you, like on the DP is going to ask you about, but you might see these more on the written test. Big thing about fronts: temperature change, wind shear, turbulence, inversions. Okay, those are all characteristics of what can happen. When may hazardous wind shear be expected? Here's your question. When stable air crosses the mountain barrier in areas of low level temperature, inversion, frontal zones, and clear air turbulence, or following frontal passage when stratocumulus clouds form indicating mechanical mixing. Which one? So, B. I agree. Hazardous wind shear, generally dealing with some type of frontal zone or low inversion. Other lifting sources. Okay.
Can we go back to that?
Yes.
So I associate lenticular clouds with fast-moving air. And
which one?
A. So stable air crosses a mountain.
Ah.
Along the layers. Yeah, I mean, when I learned how to fly, it was an easy thing to avoid. Was don't fly in a lenticular cloud because it's probably going to be windy as hell, and it might be next to some air that isn't.
Right.
And you're going to get caught in some really nasty wind shear. So what makes
totally fair. So I agree. So the question for those listening online is most power pilots are taught that he's referring to answer A, where it says flow of forming lenticular clouds, that those are associated with major winds. Well, one, I agree with you, especially because I'm going to show you where here in just a few slides where those turbulent clouds can be. And then I guess B, I don't write the FAA questions. and it's at a certain point, right? I guess these questions have to be answered as like, what is the best question or the best answer, right? So let's get to that. Other lifting sources, the ridge soaring weather, the real fun. Okay, so they're gonna in a later lecture we're gonna talk about kind of how and what are the rules to these. This is we're gonna talk about where the lift is created. So ridge soaring weather. Okay, so you generally need 10 knots or more within 30 degrees to perpendicular to good ridge soaring. Typically here in this, that's the book answer. Here in Hood River, when it's going 10 would be a little weak for here. Generally, when it's 15 knots, the ridge is kind of working. And when we say working, meaning you can stay up on the ridge. And so looking at the diagram here, as air hits it, and then it will deflect upward. Okay, so over on the back side, there's sink. So we want to stay away from that side as a glider pilot, right? The lift is up here on the front. And what I've learned, there's two places, main places to play on the ridge. There's what I call a boundary layer that's just right on the ridge, that's just 30, 40 feet up. And then there's a layer up high. And you can cruise just 30, 40 feet right above the ridge at 60, 70, 80 miles per hour, just going up and down the ridge. Okay. And then you can climb up depending on how fast the wind is. So the faster the wind hitting the ridge is, it'll deflect you up even higher. Generally, though, it does kind of level out at a certain point. It seems like I haven't been able to really get higher than like 5,000, maybe 5,500 feet above the ridge. Then I think at that point you're going to need to probably either use thermal aid or somehow leap into the wave to get higher than that, right? But there's only so much that deflecting the wind will get you up as high as it will. Okay. So, and then again, I kind of mentioned that sometimes cloud streets will build off of the ridge, or these clear lift lines, and that's total, I think, just thermal activity in line with a stable air mass and wind. But again, the ingredients are: need a long ridge, which we here in Hood River are fortunate to have, and 10 knots or more of wind almost hitting it perpendicular. Okay. Wave soaring weather. Okay. So wave soaring weather prefers also a stable air mass. Now, the books all say this. They all say stable air mass. So that means, a temperature gradient that is less than the adiabatic. But I don't buy that. I've seen the days here where it's gnarly, unstable air out there, and there's also great wave. So that, that may not be an absolute, but when you're talking to the examiner, it's like, and it's really this simple. We need a mountain range, and I need 15 to 20 knots perpendicular to the mountain range, hitting the winds. Okay, and as you've looked out, many of you've seen the waves, the lenticular clouds. They can range, as it says, 2 to 20 miles for several hundred miles away, and the air through the waves is high speed, 50 knots or more. Now, directly beneath the wave, I agree, to what Eric was saying earlier, there can be rotor clouds. There's generally three kinds of clouds with mountain waves. You'll have a cap over one of the mountains. You have the lenticular clouds showing all the different levels. And you can have rotor clouds. Now, rotor clouds will sometimes look like a cumulus cloud, but it won't be smooth on the bottom. It'll be ragged, and that's how you know that's the one to stay away. Generally, your rotor cloud, though, is kind of at the level of your tallest kind of peak, but it just depends. Like, am I playing in the wave that's behind Hood, or am I playing in the wave that's behind Mount Defiance? So it's like, now you can have a clear wave day with no, if the moisture is low in the atmosphere, you can have all this wave happening and no indication of it's even there, right? Just like those lift lines, right? So the other part to this, let me go to the next slide, which shows it a little better. Okay, so here we go. How does the wave start to happen? Well, the right atmosphere, obviously, or the right situation is a stable atmosphere with high wind speed, and the wind speed climbing, preferably climbing. And what happens is everybody here familiar with Bernoulli's principle? As air goes faster, pressure goes down. And so if this air is going faster through the atmosphere, as this hits this an orographic type region and bends the wave, this pressure goes down here, and the waves, it's even able to go faster. And then as the wind going up, you get that the waves start going, and this is what starts creating it. Questions, thoughts about that? And so, Eric, I agree. Right here is where you could enter those rotor clouds. But all beneath this, as long as is all just wave, and you can go up and down it and play in it.
Yeah, it's something I've never understood about that specific part of power. It seems really easy to teach the principle.
Right,
If you fly above or in front of it, you're probably fine.
Exactly. Yeah, and I'm like you. I came from the power world, so one, I'm learning to play in the weather like a glider, like all of the other glider pilots, and try to understand it better too. Here is this isn't really a skew T, but it is something that we use at Hood River. It has all the elements of a skew T. The reason they called it a skew T was because it was originally on paper that was skewed to the right so that it would just fit on one sheet. And so a lot of the digital charts stayed that way. But if you look at this red line here, this is the temperature for the day. And these green lines on this one are the dry adiabatic. And so this is following the dry adiabatic, which is good, and you can see the wind here on this particular day starts to increase and stays increased, right? And this was August 29th, and a lot of the pilots that flew that day, they used that chart because our mountain range, most of the Cascades, let's say they're averaging around 5,000-6,000 feet. And that was a really good wave day. And so a lot of the ways they use the skew T is not so much for the thermal index part around here, but to look for that increasing wave bar on the wind and try to predict the soaring. Okay.
About
Yep.
how high does this chart top out? I still don't.
Oh,
I don't know.
so 700 millibars is around 10,000 feet. And
Is the wind scale different for atmospheric readings
then,
than like surface reading? Because like 30 knots wind aloft at 10,000 feet doesn't sound. That sounds kind of low.
well, um, so the question for those listening is how is this chart from the ground surface readings? It's the same. It's the same. So yeah, but I guess let's say if at the ground it was 0 and at 10,000, so it's I guess, and then at 10,000 feet it's 30 knots, and if it's hitting the mountain ridge and it keeps climbing, then you can have waves. So yeah, so I suppose right. I mean, I guess you could have a calm wind day on the ground, but you got all this activity up in the air.
Yeah, I'm just used to seeing wind aloft readings.
Much higher. I agree. I agree. The comment was he's used to seeing winds aloft readings of much higher, and I agree. This does seem like a calm day for a day to have a wave. Now, I put a few pictures in here of wave. This was Corey's son, our current president, and I let him. I put the quotes in here so we knew what was going on. Here's one of my favorites. My son Levi cloud surfing 8,000 feet over the Hood River Marina last day of the season. I remember this day. Look at this. Look at this. I mean, right there, right in front of him is a lenticular, and he's just riding right on top of that. And I mean, it's just gorgeous. And then, oh, so this is a great one. Kelly sent this one. Lenny over Mosier. So here's the Lenny cloud. Okay. Here's the Lenny cloud. You can see the rotor cloud underneath. Look at the rotor cloud. This is the area you would want to stay away from, right? And it's got the indentation there. So of the draft indentation. So where the air's cruising. So you can probably pretty much go right up to that. If you touched your wing in there, probably get a little ice on it, you know, which is kind of cool. But I think that's just a fabulous picture he caught for us to see what the atmosphere is doing. So look at this one. This one is just gorgeous. This is another cloud indicating a wave. I ventured over towards where it looked like the updraft would be. I was apparently too low as it became very turbulent underneath the cloud, and I was forced to return to the ridge. So it's like reading a journal out of an explorer book. But look at that; it's just fantastic. I mean, you can definitely see the lineage. I mean, there's Mount Hood. Look at that. I mean, you can see it. Now this wave must be closer to us here. This must. I think we're dealing with a kind of an optical illusion from the camera. You can see a little bit of reflection of the cockpit here. Um, but so there's Hood. Now that one right there is definitely coming off a Hood, and that's definitely where you want to stay away from right there. But I think this must be a little closer to us, and I think that's what he's talking about. I think this is probably sitting more over Parkdale, where this is over Hood. You agree? That seems to look like that's closer to me without him here. Yeah, yeah, and then you can see all the lenticular air uh, in front of Hood. Um, we're almost done here. Okay, here are two. This was Paul took these. Paul, on November 9th, when the Lennies were spectacular, these are both taken while soaring just above them. So, um, I mean, he's just right above it. Smooth air, smooth air, and there's our valley right below it.
Do you
Um,
remember about how windy it was?
I do these days on the ground. It was 30 knots.
Wasn't that much? Because you soloed me that day, didn't you?
Was that the day I soloed you?
Yeah.
Then it wasn't that much on the ground.
You know, it kind of changed through the day.
Yeah,
It was,
there was.
I got up there and it was just, I couldn't not find lift. I was just flying over the city. You know, just the whole area was just crazy.
Got a question here from. Could you stay on the rising part of the rotor cloud? And could you stay on the rising part of the rotor cloud and would that act like ridge lift? No. But that I wanted to answer a question you had earlier, Gideon, about how you get up above the cloud streets or the thermals to break through the boundary layer. Okay, so Ian, two things. Ian, you brought up a good question here. Let me back up. So, darn. Two things. Can you stay above? Oh, the boundary cloud. Okay, so, well, what makes these clouds here, right? What makes the rotor cloud? It's we'll come back to that. The more important thing is how you get up above. What picture do I want? Oh, so let's say this here. No. Where's? Okay, here, this picture will show it. So some of the pilots have a theory, and I think they're this cloud. I think so. Some of the pilots think with some of the high winds, the wave dipping down in or dipping around, they they think there's a kind of a theory that as wind sometimes wind can hit the front of a cloud and act like its own wing, like the cloud starts to act like a wing, and you might be able to jump on air right there and climb up in front of it. So real quick, just finish because we're just about finished. There's a few. They talk about convergence lifts. Basically, with these are different ways that basically you could have an orographic region where air could come around two valleys and meet and create air, an updraft of air, right? Such as this, and maybe here on the right side, there's like a city here and it has, or there's a lake or something, and it will have carry water with it, and then they'll meet and they'll create like a cumulus cloud, and you can see the convergence, right? So now this is an interesting phenomenon. It happens here in Hood River, and that's sometimes towards the end of the day, a valley convergence here, especially as the east side of the west mountains there start to cool. The sun's gone down over here, so if Hood River sat here in the middle, this air will cool off and start coming down, and it'll create this lift all over the valley at the end of the day. It's called a Katy drainage wind. It's not a little bit unlike the wind you mentioned earlier, and I've heard some people call it a glass wind. It's very smooth and kind of carry it's like the last flight to carry you home towards the end of the day. It is. It is. Yeah, it is enough to sustain flight. Let me see what we got left. All right, a few questions here. During which period is a sea breeze front most suitable for soaring flight? Shortly after sunrise, during the early forenoon, or during the afternoon? And that's going to be during the afternoon. We didn't really get to talk about that, but sea breezes as the air on the surface of the near the sea warms up, the cool air. What? The cool air, you know, that air heats up, the cool air will blow in, right? Because that's dense air over the land, and the cool air it's colder air, so it's gonna want to fill in that pressure. Um,
Why can't you fly back and forth on the upwind side of a rotor cloud?
oh, oh,
It's not
it's not smooth.
smooth.
It's not smooth. Actually, I was gonna talk about how that cloud forms, but it's not that exciting. Um, so, all right, so we are at 9 o'clock, which is our end time. Let me see how much we have left here, and it's up to you guys if you want to finish this last part out or save it for next week. Keep going. All right, Eric. Keep going. So explains hazards associated with flight in the vicinity of thunderstorms. I'm going to make this. Conditions required for thunderstorms: moisture, an unstable atmosphere, and a lifting source, right? So moisture, that's an easy one. Water vapor, hot summer months, right? And then a lifting source. So mountains, air, uh, thunderstorm life cycle, cumulus stage. Actually, the only reason I kind of put these in here is because they ask a few questions on the written test, right? So cumulus stage looks like any other cumulus, except it's going to grow into it's going to have continuous updraft. The mature stage, that's where the rain, the hail, the lightning, the thunder, that anvil shape starts coming in, and then the dissipating stage. It's where the heaviest rain comes in. The strong, widespread downdrafts, microburst, things like that, right? So here's the questions. Which weather phenomena signals the beginning of the mature stage of a thunderstorm? The appearance of an anvil top, precipitating beginning to fall, or maximum growth rate of the clouds? Precipitation. That's right. Okay, so here's really the key point to this. Thunderstorm hazards, avoid them because they move very fast, right? Turbulence, moderate within several miles, fly within VA. The non-pilots here yet, or the guys that haven't started flying yet, VA is a speed we'll be talking about, or V speeds. It means maneuvering speed. So anytime you're in severe turbulence, your aircraft will have a maneuvering speed that you want to get it down to, and then try to maintain straight and level flight. Strong up-down drafts, shifting surface winds, wind shear, microburst. Again, the question was, they want you to know, what are the hazards of flying within or near a thunderstorm? So these are the big ones: the wind shear, the microburst, gust fronts up to 60 knots. Hail, that's not very friendly to aircraft. Poor visibility, so you could lose situational awareness. Lightning, you you can't outrun a lightning. You can't outrun lightning. Tornadoes, squall line, multi-cell thunderstorms. Squall lines are, they're just long strings of thunderstorms, and they present the most intense hazard to all aircraft. The reason I put that is because they will ask you that. which is considered to be the most hazardous condition when soaring in the vicinity of thunderstorms? Static electricity, lightning, wind shear, and turbulence. C. Good job. Wind shear and turbulence. Thunderstorms, which generally produce the most intense hazard to aircraft, are squall line thunderstorms, steady state thunderstorms, warm front thunderstorms. A. Good job. Is there a thunderstorm activity? If there is a thunderstorm activity in the vicinity of an airport at which you plan to land, which hazardous atmospheric phenomenon might be expected on the landing approach? B. Wind shear turbulence. All right, so, whew. Sorry for the first part of that. Okay, so next week, this is one of my favorite pictures because we're going to talk about how to forecast weather, how to find weather information. And in this particular picture, I was at the Astoria airport. I've got my iPad. I've got ForeFlight, which is a program I use to depict weather. And you can see in the green there, it's telling me the visibility is 10 statute miles. The green all means it's clear, and I'm looking out at the Coast Guard helicopter. I can barely see the runways beyond it. So I love this photograph because sometimes the weather information's a few minutes behind, and here it was definitely a few minutes behind. So and then just two more pictures after this. This is cool because this is from Tim. Oh, so again, these two photos, just read this real quick. This is a very typical of the cloud formations on a great day of soaring in the Hood River area. Kelly wrote this. Photo was taken on April 27th. I'm at approximately 9,500 feet stationary in a section of wave located over Cooper Spur Resort. You were looking north at Tim's plane, which is here. In the center of the photo, just above the clouds, left of his plane is Mount Adams and Rainier. You can see Adams and Rainier right there. This day was the day after a front had passed. The jet stream remained over our area, and there was still a bit of moisture in the atmosphere with quite a few cumulus clouds lingering. You will notice the cumulus clouds immediately thin out to the east. If you could see west, there would be a heavy cumulus, perhaps a solid wall starting at Mount Defiance. The cumulus cloud base was approximately 5,500 to 6,000 feet, which is typical in these conditions. The surface wind was 15 to 20 out of the west. Winds aloft were 20 to 30 knots from the west. So not as, only, and that's common to see that big wall up there. And then his second page was, oh, this is a great part. So we used all three types of lift this day in order to finally soar in the wave. First, we are towed to the east ridge, released at approximately 2,000 feet. The cumulus clouds are moving quite quickly, being blown west to east, passing over our ridge and disappearing completely before reaching the Dalles. You're using the lift generated by the ridge to get around 3,500 feet. While hanging out on the ridge, you can take time to study the passing cumulus and the lenticular clouds that are forming at higher altitudes. As you can see from the photo above, the lower cumulus clouds start to form into rows or small areas of streeting. And I showed you that, and you can see some here, but the other picture was better for it. There's thermal or convective lift located under these cumulus clouds. The base of the cumulus on this day were around 55 to 6,000. On this day, the lenticular are forming at around 14,000 feet, which usually indicates the top of the wave lift. There are specific spots located throughout the Hood River, Parkdale, and Underwood areas that have been identified over the years as good places to hook into the wave at lower altitudes. When you see an opportunity, you can leave the ridge lift and fly under the cumulus cloud and thermal lift to finally reach an area of wave lift. So there you go, the Hood River trifecta. Yeah, I remember him talking about that one street, right here. I've also heard of them talking about if you can get over into here off of this street, just kind of above like the fairgrounds, the wave actually kind of dips down in there, and you can kind of just, but you kind of got to know like to feel it, and then it'll take you up, you know. So thanks, guys. Appreciate it. Next, and any questions, thoughts, concerns, write them to me. Next week we'll do it again and have more fun. And we're getting closer week by week to the soaring season.